Every year, the world spends over $2 trillion patching, reinforcing, and replacing crumbling concrete. You heard that right, $2 trillion every single year. Enough to build the entire U.S. interstate highway system from scratch, more than 6 times over. And China just made most of that spending obsolete. That is just the beginning, and the part nobody is talking about is not the concrete that heals itself, it is what happens to the country that controls it. If that sounds like the kind of thing that should be front page news everywhere, hit a quick like and subscribe so you don't miss the next one. By the end of this video, you are going to understand exactly how a material that fixes its own cracks is about to redraw the economics of civilization itself. Here is where it starts, with the oldest and most catastrophic design flaw in modern construction. Picture the most important material in the world. Not gold, not silicon, not oil. Concrete. You are surrounded by it right now. The floor under your feet, the road outside your window, the bridge you crossed this morning without thinking twice. Concrete is the second most consumed substance on Earth after water. Every single year, humanity pours roughly 10 cubic miles of the stuff. That is enough to bury the entire state of Texas under a layer more than a foot thick. And almost all of it, every bridge, every tunnel, every dam, every skyscraper foundation, starts failing the moment it is finished. Not dramatically, not all at once. That is the part nobody tells you. Concrete does not collapse. It creeps. It develops hairline fractures so small you could not fit a human hair inside them. And then those fractures widen. Water gets in. In cold climates, that water freezes, expands, and pries the crack open further. In coastal cities, salt water carries chloride ions deep into the structure, where they attack the steel reinforcement hiding inside. The steel rusts, it swells, and eventually the concrete surrounding it spalls off in chunks. Civil engineers have a name for this. They call it concrete cancer. And it is eating the infrastructure of every developed nation on Earth right now, while most people have no idea it is happening. Here is the detail that puts everything into perspective. The American Society of Civil Engineers estimates the United States alone has over 600,000 bridges. That is more bridges than there are towns in France, Germany, and the United Kingdom combined. Nearly 42% of them are over 50 years old. More than 7,000 are rated structurally deficient. You drive across them, your kids ride school buses across them, and the maintenance backlog to bring them up to standard runs into hundreds of billions of dollars money that most municipalities simply do not have. This is not an American problem. This is a civilization problem. Europe is staring down the same curve. So is Japan. The design life of standard reinforced concrete is somewhere between 50 and 100 years. Everything built in the 1950s, 60s, and 70s is already at or past its expiry date. Here is the brutal catch. The cost of fixing a crack when it is 1 millimeter wide is roughly 10 times cheaper than fixing the same crack after it has grown to 10 millimeters. And 100 times cheaper than replacing the structure entirely. But inspection cycles are slow, budgets are thin, and concrete does not send you an alert when something goes wrong. That is the world China looked at. And instead of building a better inspection system, they asked a completely different question. What if the concrete could just fix itself? But understanding why that question is so radical requires understanding something most people never think about: what concrete actually is, and why cracking was always written into its DNA from the very first pour. Most people think concrete is just gray rock you pour into a mold. And that mental model is exactly why the failure mode surprises everyone. Concrete is not rock. It is a chemical reaction that never fully stops. And once you understand that, the cracking stops looking like a defect and starts looking like an inevitability. Here is how it actually works. You take cement, a fine powder made primarily from limestone superheated to around 2,700 degrees Fahrenheit, hot enough to melt copper, and you mix it with water. The moment those two things touch, a reaction begins called hydration. The cement particles dissolve and recrystallize into interlocking needle-like structures that give concrete its compressive strength. A standard concrete column can handle pressures of 4,000 pounds per square inch. That is roughly the pressure at the bottom of a swimming pool, multiplied by nearly 300. But here is what most people get wrong. That crystal structure is brittle. Think of a china dinner plate. Incredibly hard, holds weight beautifully, but drop it once and it shatters. Concrete under tension being pulled apart, bent, or twisted behaves almost exactly the same way. So engineers compensate by embedding steel rebar inside the concrete. The steel handles the tension, the concrete handles the compression. Together they form reinforced concrete, and that partnership built the modern world. The problem is the partnership has a fundamental incompatibility built into it. Steel and concrete expand and contract at slightly different rates when temperatures change. On a hot summer day in Phoenix, the surface of a concrete bridge deck can reach 150 degrees Fahrenheit. By winter, it can drop below freezing. That temperature swing, cycling hundreds of times over the life of a structure, creates micro-movement at the steel-concrete boundary. Over years, those micro-movements accumulate, cracks form. And once a crack opens, the protection the concrete provided to the steel is gone. Now here is the part that engineers don't want to admit. The very process of concrete curing causes shrinkage. As the crystals form and water is consumed, the material contracts slightly, which means every concrete structure ever poured arrived at its first day of service already carrying micro cracks. Not from load, not from weather, from simply becoming concrete. The failure begins before the first truck ever drives across the bridge. For over a century, the response was to add more rebar, more sealant, more inspection cycles, more maintenance crews. The entire field of civil engineering built a vast and expensive system to manage the inevitable decline of a material it never figured out how to stop from declining. Until someone asked whether the solution was already alive and had been alive for 3.5 billion years. Imagine you cut your hand. Not badly, just a small nick. You do not call a doctor. Your body detects the breach, sends resources to the site, and seals it from within. New tissue forms. The wound closes, and within days, you have forgotten it ever happened. Now imagine concrete that works exactly the same way. That is not a metaphor. That is precisely what Chinese researchers built, and the mechanism behind it is older than almost every living thing you have ever seen. The organism at the center of this is a bacterium called Bacillus specifically, strains that survive in environments with a pH above 12. That matters enormously because fresh concrete has a pH of around 12 to 13, more alkaline than bleach, an environment that kills most living things almost instantly. But certain Bacillus strains evolved in highly alkaline natural environments, volcanic lakes, mineral springs, the deep subsurface, and developed a survival mechanism that makes them uniquely suited for this application. When conditions become hostile, they form spores. Think of a spore like a seed inside a vault. The bacterium compresses its genetic material into a protective shell so tough it can survive temperatures above 250 degrees Fahrenheit and complete desiccation for decades. The spore asks for nothing. It consumes nothing. It simply waits. Scientists have successfully revived Bacillus spores dormant for over 25 million years, recovered from the gut of a prehistoric bee preserved in amber. When researchers embed these spores into a concrete mix along with a calcium-based nutrient compound that serves as their food source the moment they wake, the spores survive the mixing process, the heat of hydration, and sit dormant indefinitely. The structure goes into service. Years pass, decades potentially, and nothing happens until a crack forms. When a crack opens, moisture and oxygen enter. Those two triggers are all the spores need. They germinate. The bacteria wake up, metabolize the calcium nutrient compound, and produce calcium carbonate as a byproduct. Calcium carbonate is limestone, the same mineral that forms stalactites, that makes up coral reefs, that constitutes the White Cliffs of Dover. It precipitates directly into the crack, crystallizing as it forms, filling the gap from the inside out. Now, here is the part that blows people's minds. The crystals grow to conform to the geometry of the crack, bonding to the existing concrete on both sides. The repaired zone does not just look sealed. Under analysis, it shows compressive strength comparable to the original matrix. The crack is not patched, it is healed. Chinese research institutions demonstrated crack closure in widths up to 0.8 of a millimeter, roughly the width of 8 sheets of standard printer paper, stacked together within 28 days of moisture exposure. Without any human intervention, without any external material applied, the structure did it by itself. But knowing the biology works in a laboratory is one thing. Getting it to survive inside a real concrete pour, with real industrial timelines and real structural loads that required solving 3 problems at the same time. And solving them pushed Chinese engineers to the edge of what materials science currently knows how to do. You now know what the bacteria do. But keeping them alive long enough to do it is where the story stops being about biology and starts being about engineering precision that only happens when a government decides something is a national priority. The first problem was survival during mixing. Industrial drum mixers generate enormous shear forces inside the mix. The aggregates, the sand and gravel that make up the bulk of concrete, are hard and abrasive. They collide constantly, and the temperature inside an active mix can spike to over 140 degrees Fahrenheit in the core of a large pour, hot enough to kill most bacteria outright if exposure is prolonged. The solution was encapsulation. Think of a standard gel capsule, the kind that holds cold medicine, a thin shell protecting the active ingredient until it reaches the right environment. Researchers developed microcapsules made from silica gel, expanded clay, and polymer shells, each smaller than a grain of fine sand. The spores and nutrient compounds are sealed inside before the concrete is ever mixed. The capsule absorbs the mechanical abuse of mixing, shields the spores from peak hydration temperatures, and remains intact until a crack physically ruptures it. The rupture releases the spores. The spores meet moisture. The healing begins. But the capsules had to be weak enough to rupture when a crack passes through them, yet strong enough to survive decades of structural load without rupturing prematurely. That tolerance window is extraordinarily narrow. Too strong and the crack passes right through without releasing anything. Too fragile and the mixing process destroys them before the concrete sets. Here is what makes this incredibly exciting. The calibration is not universal. Different concrete mixes need different capsule formulations. Chinese research teams mapped that entire matrix, not just for 1 or 2 mix designs, but for the full range of concrete grades used across national-scale infrastructure construction. The third problem was longevity. A bridge built today might be expected to serve for 100 years. The bacteria need to remain viable for that entire period, dormant, protected, ready to activate on day 1 or day 36,500 with equal reliability. Research teams stress-tested encapsulated spores under accelerated aging conditions and modeled projected viability curves over multi-decade timeframes. The data suggested viable dormancy well beyond 50 years under normal service conditions. The honest answer from the researchers themselves is that the concrete will likely reach the end of its design life before the bacteria do. Now here is the part that nobody talks about. All 3 problems were solved concurrently, not sequentially. Biology teams, materials science teams, and structural engineering teams worked in parallel, sharing data in real time. That coordination model is not glamorous, but it is the reason this technology moved from peer-reviewed paper to poured structural concrete faster than any comparable materials innovation in recent memory. And fast is precisely the word. Because what China did next was not run another laboratory trial. They built with it, at a scale and in conditions that no laboratory could ever replicate. And the results rewrote what engineers thought was possible. There is a difference between a technology that works in a laboratory and one that works when 10,000 trucks are driving over it, and the consequences of failure are not a failed experiment, but a collapsed bridge. China did not ease self-healing concrete into service on a quiet rural road. They deployed it into some of the most demanding infrastructure environments on the planet. The starting point was highway infrastructure. China's national highway network stretches over 100,000 miles, a distance equivalent to circling the Earth 4 times at the equator. Sections running through Heilongjiang Province, where winter temperatures regularly drop to -40 degrees Fahrenheit and freeze-thaw cycling is among the most severe road environments on Earth, were selected as early deployment zones. If the material could prove itself in Heilongjiang winters, it could prove itself anywhere. Inspection data showed measurable crack closure in surface fractures that in standard concrete would have required intervention within 1 to 2 seasons. The cracks appeared, the bacteria activated, and the surface sealed without a maintenance crew ever touching it. From roads, the application moved into tunnels. Tunnel repairs are enormously expensive, not just because of material cost, but because of traffic disruption. Closing a major tunnel can cost a city more in economic disruption. Repair itself. Chinese infrastructure projects in Guangdong and Zhejiang provinces incorporated bacterial concrete into tunnel lining sections, with monitoring programs tracking crack behavior over multi-year windows. Closure rates aligned with laboratory projections and in some cases exceeded them because the tunnel environment provided a consistently humid microclimate that kept activation conditions near optimal. Here is the detail that reframes everything you just heard. The real validation was not crack closure rates. The real question was structural. Did the healed concrete actually carry load the way uncracked concrete does? Chinese engineering teams subjected healed samples to compressive and tensile testing after bacterial repair cycles. Results showed repaired zones achieving between 70 and 90% of the original compressive strength. In some optimized formulations, the healed zone reached full original strength. That number matters more than any other in this story. 70 to 90% strength recovery means a self-healed structure is not just aesthetically restored, it is structurally restored. The load path through the material is re-established. If the scale of what China is building with this surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. The science behind self-healing concrete did not start in China. The foundational research was pioneered in the Netherlands. A microbiologist named Henk Jonkers at Delft University of Technology spent years in the early 2000s identifying alkaline-tolerant Bacillus strains, proving spore survival in concrete matrices, and demonstrating calcium carbonate precipitation inside cracks under laboratory conditions. That work was rigorous, peer-reviewed, and genuinely brilliant. Jonkers was awarded the European Inventor Award for it. The European research community built something real. And then, largely, it stayed in the laboratory. That is not a failure of imagination. It is a failure of translation. The gap between a proof of concept and a deployed infrastructure material is not a scientific gap. It is an institutional one. In Europe and the United States, the pathway from university research to construction industry adoption runs through private material suppliers, independent standards bodies, risk-averse procurement frameworks, and liability structures that make specifying an unproven material in a public infrastructure project an act of considerable professional courage for the engineer signing off on it. The incentive system does not reward early adoption. It punishes failure. American institutions, including MIT, produced parallel bodies of work on self-healing concrete using different mechanisms. The science was credible. The funding was real, tens of millions of dollars across American universities over 2 decades, tens of millions of dollars and 0 highway miles of deployed material. Here is what most people get wrong about why China moved faster. The common assumption is that authoritarian systems mandate technology adoption and skip the validation process. That is not what happened. Chinese researchers did the validation. They ran the laboratory trials. They published the papers. What they did differently was run the institutional translation process in parallel with the science. While biology teams optimized bacterial strains, standards teams were already drafting technical specifications. While encapsulation engineers calibrated capsule wall thickness, procurement frameworks were being updated to accommodate performance-based concrete specifications. The science and the system evolved together. China's Ministry of Transport has direct mechanisms for fast-tracking promising construction technologies from research designation to approved material status. And when state infrastructure investment runs at the levels China has sustained over $20 trillion across the past 2 decades, a figure that dwarfs the GDP of every nation on Earth, Except the United States and China itself, the procurement volume available to validate a new material at scale is simply without parallel anywhere else. Now here is the part that changes the entire frame of this story. European researchers invented a concept. American researchers expanded it. But the country that turns a concept into a deployed standard writes the specification the rest of the world eventually adopts. Construction material standards are not just technical documents. They are market access instruments. When bacterial concrete specifications developed by Chinese standards, bodies are exported through Belt and Road infrastructure projects across 68 countries. The contractors building those projects, the engineers certifying them, and the governments procuring them all operate inside that standard. The technology transfer and the standards transfer happen simultaneously, and once standard is embedded in a nation's infrastructure procurement system, replacing it is a decade-long project. China is not just building self-healing bridges. China is building the definition of what a bridge is supposed to be. And that definition is about to go global in a way that makes everything else about this story look like a warm-up act. What just happened in Chinese laboratories and on Chinese highways is not a construction story. It is not even an infrastructure story. It is a story about who gets to define the material conditions of the next century and what it costs everyone else when they do not. Concrete is the substrate of civilization. Every hospital, every power plant, every port, every runway, every dam, holding back a reservoir, a city, depends on all of it, sits on concrete, or is made of concrete, or is held together by concrete. When you change what concrete does, you change the economics of everything built from it. And the economics here are not marginal. They are transformational. Here is the number that reframes everything. The global infrastructure maintenance deficit, the gap between what governments spend on existing structures and what those structures actually need, is estimated at over $90 trillion. $90 trillion. Larger than the entire global economy. Every tax dollar collected, every sovereign wealth fund combined, and it still would not cover the bill. That deficit is not a funding problem at its core. It is a materials problem. Concrete that requires constant intervention to remain functional is concrete that generates liability faster than it can be managed. Self-healing concrete changes that curve dramatically. If bacterial concrete extends the effective service life of a structure by even 20%, a conservative figure based on current field data, the maintenance cost reduction over a 100-year infrastructure portfolio runs into the tens of trillions of dollars globally, not billions. Trillions. And that calculation does not include the secondary value of structures that stay in service without the traffic disruptions that major repairs generate. A bridge that heals its own cracks saves the repair cost. It saves every lost hour of productivity from the traffic jam the repair would have caused. The value compounds in ways that standard infrastructure accounting almost never captures. Now, here's the part that engineers don't want to admit out loud. The structures going up right now, in every city in the world, the ones using standard concrete, are already on that depreciation curve. Already accumulating micro-damage. Already moving toward the maintenance cliff that their municipal budgets are not prepared for. Every structure poured with conventional concrete from this point forward is a future liability. And every structure poured with self-healing concrete is a different kind of asset, one that actively defends its own value over time. Here is what makes this an entirely different kind of geopolitical moment. Infrastructure has always been the physical expression of economic power. The Roman Empire did not just conquer territory. It paved it, bridged it, and aqueducted it. And Roman road standards became the template European builders referenced for over 1,000 years after Rome fell. British railway gauge standards. American highway design specifications. The ISO container dimensions that made modern global shipping possible standardized in the United States and adopted by every port on Earth within 2 decades. The country that built the infrastructure wrote the rules for how infrastructure was built. China is executing the same playbook with self-healing concrete. Belt and Road projects across 68 countries are already specifying Chinese construction materials and Chinese technical standards. When self-healing concrete specifications become the baseline for infrastructure built across Africa, Southeast Asia, and Central Asia, as the construction volumes and contractor relationships strongly suggest they will, the economic relationship embedded in every one of those structures runs back to the country that defined what the concrete inside them is supposed to do. The $2 trillion the world spends every year patching crumbling concrete is not just a waste, it is a vulnerability. It is the ongoing cost of building a civilization on a material that was always designed to fail slowly. China looked at that vulnerability and engineered a way out of it. And in doing so, they did not just solve a construction problem. They repositioned themselves as the country that holds the patent on how the physical world maintains itself. The concrete under your feet right now is cracking, slowly, invisibly, inevitably. The only question left is who decides what comes next and whether the rest of the world moves fast enough to have a say in the answer. If this changed how you think about what is actually whole, world together, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Do you think Western nations will develop and deploy their own self-healing concrete standards in time to compete? Or has China already locked in an insurmountable lead? Make your case below